Hello, we are Capstone Team 1 working on a bioartificial liver support device for our client and mentor, Dr. Warnock. I'm Julie, and here are my group members, Bill, Garrett, Sundus, and Sarah. Acute liver failure is characterized by sudden and rapid loss of liver function in patients with no pre-existing liver disease. Current treatment options are limited to liver transplants or drug treatments to reverse the effect of toxin buildup. Our team aimed to design an extracorporeal bioartificial liver support device that can perform the liver's essential functions, including detoxification, regulation, and synthesis of glucose, lipids, cholesterol, amino acids, and proteins. The conceptual design selects adequate device components for a bioreactor, and our mathematical model addresses oxygen transfer. From this general schematic, an emphasis was placed on the design of the bioreactor component. Rationale for the type of bioreactor, cell, and biomaterial can be explained as follows. Primary human hepatocytes were the cells chosen because they ascribed with performing most of liver-specific functions. Using our design matrix, a hollow fiber bioreactor was selected as it has a large surface area to volume ratio, efficient exchange of nutrients, and immune isolation. From our biomaterials, we picked PES with a collagen-coated PLLA high-performance engineering thermoplast. The final bioreactor design is a cross-hollow fiber bioreactor containing primary human hepatocytes in the extraluminal space. The cross-fiber design increases hepatocyte viability by addressing the issue of insufficient oxygenation that plagues current devices. PET packing was added to the design to ensure that anchorage-dependent hepatocytes can achieve a high concentration within the extraluminal space. The bioreactor was sized to ensure it can support the growth of a number of hepatocytes equivalent to 10% of total liver mass.
We found that it is too computationally expensive to create a model for the crossed hollow fiber configuration. Thus, we modeled the plasma and oxygenation streams as independent standard hollow fiber bioreactors. Since oxygen has historically been the limiting substrate in bioartificial systems, we analyzed the oxygen consumption rate of each individual hollow fiber or capillary. Furthermore, it was assumed that the cells occupied only the space within a certain radius around the outer surface of the membranes, and that the PET packing would not impact oxygen transfer. The model we adapted from literature includes 4 coupled ODEs as seen here. The first ODE represents the axial gradient of pressure through the system. Second is the fluid pressure at position Z along the axis of flow. Third, we have the volumetric flow rate into the extracapillary space from the lumen. Finally, we have the oxygen consumption rate. All of these ODEs are modeled as functions of axial position Z. In this diagram, the blue line represents the plasma stream while the orange represents the oxygenation stream. The oxygen consumption rate, or OCR, in the high oxygen stream peaks much further down the longitudinal axis of the bioreactor than that of the plasma stream. The peak OCR of the oxygenated stream, however, is significantly higher than that of the plasma stream. Since a higher OCR indicates and allows for greater metabolic function of hepatocytes, it is clear that the inclusion of a perpendicular oxygenation stream would significantly increase the efficacy of the bioreactor. In comparison to a standard hollow fiber bioreactor, only perfused with plasma, it would provide all of the cells with more oxygen. The chart below shows the characteristics of the model output with differing partial pressures of oxygen in the inlet stream. When entering the liver, blood typically has an oxygen partial pressure of 76.8 millimeters mercury. Given this partial pressure of oxygen, 100 grams of liver mass is able to consume 21,945 nanomoles per minute of oxygen. Since the peak consumption rate per capillary was determined to be 0.12976 nanomoles per minute, with the partial pressure of oxygen of 76.8, the number of capillaries required would be astronomical at 169,120 capillaries. Alternatively, using an oxygenated inlet stream with a partial pressure of oxygen of 375 millimeters mercury, 100 grams of liver mass could consume 107,000 nanomoles per minute. While this is substantially higher than the non-oxygenated stream, the consumption rate per capillary is much greater at just under 3 nanomoles per minute. This would require the use of 38,057 capillaries to match oxygen consumption of 10% of the liver. In the process of finding models to base our model off of, we discovered several limitations associated with the computational modeling of bioreactors. First off, with complex fluid flow, modeling is computationally expensive and many models are simply unsolvable. For models that do provide a solution, there are often several approximations that reduce accuracy, especially when new levels of complexity are added, such as additional streams. For more accurate depictions of bioreactor fluid flow and kinetics, sophisticated partial differential equation solvers are required. For the most accurate results, modeling should be coupled with experimental results. The in vivo model can further be tested for efficacy by testing for proper levels of albumin, ALAT, and ASAT. Thank you.